Buenas tardes. Damos inicio a nuestra segunda jornada de...
This is the beginning of our second session of today, the second day of our International Congress on Ship Design and Naval Engineering, to continue the topics on design and production of ships. The first presentation this afternoon is going to be done by Mr. Gerardo Morales Barbosa from Universidad Nacional de Colombia. Mr. Barbosa is currently undergoing the mechanical engineering program in the university's Medellin site. He has experience in naval design and he's performed since 2019 as the coordinator of fluid mechanics for the research center at such university. His presentation is entitled Aerodynamic Study of the Hulls of an Electrical Catamaran for Racing. Okay, my name is Johan Morales Barbosa, and my presentation was done along with the participation of engineer Romero Nieto. We're going to be looking at the structure on screen. First, we're going to see why the paper was developed and what motivated it, by looking at some advanced resistance studies and the importance of this information within the context of the presentation. Then we're going to be looking at some general studies within the article. And then we will do the case study defined by explaining the model for the selected ship and the parameters taken into account for the simulation. And finally, we're going to talk about the studies done after the simulation. Okay, the initial motivation was born out of Universidad Nacional, where due to the invitation to participate, a group of students motivated by the creation of alternatives to contribute to the sustainable mobility created a group called Hidrometra. This is not far from the reality of the current world, and about 80% of global trade is moved through maritime routes, which is an important scenario for energy efficiency in the naval context. When building a ship, it is important to look at the drive resistance. It is one of the factors of the highest influence. It is a force opposing the motion of the vessel or any type of body. It is important to study this because basically it is an energy expenditure generated by motion from one point to another. It occurs in ships, cars, planes, and even people when they walk. It all depends on different factors, namely the geometry of the item, the speed at which it moves, and the density of the fluids in which the body is embedded. This last one is very important because it actually makes for the main argument, given the difference in terms of three orders of magnitude of the elements around a vessel, which is basically water and air. The studies carried out for the design of the hulls of a ship only focus on the water. The purpose of this paper is to calculate both contributions separately and compare one to the other with the purpose of getting accurate values in terms of the contribution of each fluid. In terms of drive resistance, how can that be calculated? And there are different ways, depending on the methods and the precision of the results. We have the empirical methods, which basically consist of functions that have been obtained by means of empirical tests or trials of a hydrodynamic nature. On the basis of those tests, some data were obtained, and graphs on the basis of polynomial equations were generated depending on the model selected for the vessel or the craft that we're studying. This method is always very accurate as long as the geometry of the vessel is similar to the geometry being used for doing the tests on the channel, which isn't always the case. So we have CFD, which is a tool. It is a branch of fluid mechanics, which is comprised of a method on the basis of which we use numerical approaches to calculate the movement of fluids around the vessel. And later on, we'll talk about this in further detail. And finally, we have the hydrodynamic SA channel, where we generate a vessel at scale, we put it on a water channel, and we move it through a sensor-based mechanism that allows us to practically calculate the contributions or the inputs, including drive resistance. As we can see in this presentation, the results vary in terms of precision, because here we depend a lot on the fact that our hull has to be similar to the hydrodynamic hull. The precision increases, it jumps, as indicated by the arrow, and the cost also goes up. Empirically speaking, all we need is a software, which is actually quite simple, and it is a considerable computational power. And the most expensive part of the model is the channel as such. Okay, CFD, I'm going to give you a very simple explanation. This is an element of finite fluids that actually allow us to determine the interaction of fluids on a body moving within the fluid. CFD basically divides the region of the space where the fluid is going to be moving, or the vessel is going to be moving rather. And it calculates the properties of that fluid in small space regions, ever smaller. We give the CFD an Eulerian approach because it involves reference systems that are still, and we don't actually follow the particle on an individual basis. The algorithm that we use for this paper is going to be explained later on. The definition of the geometry actually consists of, okay, we define what the vessel was, and we also define the control volume of interest. The part of the meshing was divided in terms of smaller volumes so that the analysis could be more accurate. The definition of models selected the models of turbulence and the equations that are going to be defined, and the analysis of results after doing the simulation. Here we can analyze what was obtained. Okay, before we go about what happened to the vessel, we have to see why we selected it. And it was selected because in the hydrometra group, this vessel was already there. It had been manufactured for the Hydro Contest 2017. However, during the design process, we only applied the empirical methods for evaluating the hydrodynamic performance. And here you can see some pictures of the vessel as such. This was at the Guatapé Nautical Club, where the members of the group actually tested the vessel once it was manufactured. Here we can see the ship. And having said this, the general characteristics of the vessel, well, it is a catamaran, and the hull is basically a couple of tubes upon which we assemble the control boxes. We have a total length of 2.39 meters, total width 126 meters, the hull width is 0.15 meters, and the other dimension. We define the geometry, keeping into account the CAD of the ship, very judiciously put together. And it is important at this point to look at the models to avoid any problems during the meshing. So we can see that the vessel that we originally had, the one that was manufactured, is actually far from the model that we used for the simulation. However, the hydrodynamic factors were actually maintained in essence. That's why we decided to remove the rudder and the propeller, because they didn't quite contribute to the performance of the hull as such. Okay, on this slide, I show some of the simplifications applied. First, we removed some of the round items and some of the blank items, which ended up becoming something quite compact. It's not exactly the real thing, but it's close to it. Some of the other elements were removed, such as bolts and washers, because they weren't considerable in terms of the hydrodynamic performance of the vessel. Upon definition of the geometry of the hull as such and of the vessel as such, we applied a condition of symmetry. And as it is a catamaran, we can go down the mid-plane and there is symmetry. And once we've defined this, which is the final part that's going to be simulated, we didn't put this into the software. What we entered was the domain, which is the control volume around the vessel. As we can see here, right down the middle, we can see the walls of the simulation, basically the vessel as such, and we studied the air or the fluid around the unit. Okay, here we can see the factors that were taken into account to do the dimensioning of the control volume. Basically, from the frontal end, we left 5 points of length along the plane where the fluid goes in, with the purpose of the fluid developing well prior to its coming into contact with the vessel. We took into account more than 3 lengths on the side of the vessel to avoid reverse flows due to the turbulence after having collided into the vessel. The other values were arbitrary. We left sufficient space because due to the turbulence there may have been a reverse flow coming onto the walls. Okay, once the geometry to be entered into the software was defined, we then moved on to the meshing. The meshing, again, is discrete in terms of the control volume that we want to target. So the volume is actually very small so that we can study the behavior in each bit of volume. The meshing, the model for this vessel is made up of 3 different types of cells. The hexaedric cells are shaped like cubes, and it can be put at spots that are away from the vessel because because fluid is not considerable here. Tetraedrical elements were discarded because of the complex geometry of the vessel, so we defined only a few tetraedrical elements, and at the spot closest to a wall, we refined the boundary layer. And the dimensions of that boundary layer and their cells were calculated taking into account different factors such as the speed of the vessel and the total length of the vessel. Upon definition of the meshing, once we obtained the meshing, we had to also define the models. As I was saying, it defines the equations that are going to be resolved in each cell. So there are different types of models, each with different pros and cons. What happens with the models is that they have a higher mathematical complexity depending on what we want to accomplish. As we can see in this picture, the one used was a model of matter stocks by Reynolds and a model that has good behavior in areas close to the walls, and that's what we're interested in terms of drive resistance. There are different types of models depending on the accuracy of the results obtained, as I was saying, and also depending on the computational cost. As we can see here, we utilize RANS, which is the most widely known one. And what it does is to get an average of any type of turbulence. So as we can see here, in terms of the development of the flow, there is no turbulence at any point. There is another type of modeling, which could be the large vortex modeling that only considers the largest vortices within the fluid, and also DNS, which is basically a straightforward numerical solution considering all of the vortices covered, but due to the level of accuracy that was required and the computational resources available, we decided to go with the RANS model. Okay, and after several iterations and other processes for this first simulation, we did 2 simulations, and depending on the draft. The first draft was 0.11 meters, and the contact and the area of contact with air accounted for about 72% of the total area of the vessel, and the water accounted for about 9%. Having said that, the drag due to pressure is still very large considering water and air. So about 15% to 85% compared to air and water. And also, drag due to friction, the drag by water is more considerable despite the fact that the contact area is a whole lot smaller. In the next simulation, simulation number 2, we also utilize a draft of 0.12 meters. This was based on the models obtained by something that is realistic. And again, the values, the area of 0.62 against 1.33 is still approximately more than double the area of contact with air, but the drag due to pressure and due to friction is still considerably higher in the case of water. However, considering that the difference in density is around 3 orders of magnitude, the resistance is not what we expected, which is something considerable. Okay, as for the conclusions, this simulation was done for an unmanned catamaran. It was basically a couple of tubes and 2 control boxes. The aerodynamic effects on a larger vessel or a vessel of a different purpose could actually be bigger. And in the industry, this is quite considerable, taking into account the drag generated by the air. Obviously, we're clear on the fact that the speed and the draft of the vessel end up becoming determining factors for the level of the force of drag generated by each of the fluids The design always needs to take into account drive resistance. It is an equation of energy efficiency, energy savings, and it is a priority in the current world. As for future work, we hope to consider, as I said before, vessels with a contact area that is a whole lot larger. And we need to take away pressure from the simulation, for instance, adding trimming or a dynamic meshing to try and study the movement of the vessel. Also, we hope to analyze different speeds within the simulations with the purpose of studying how the speed change behaves with the drag from every single fluid. And that's the end of the presentation. Thank you. Okay, Johan, thank you so much for your presentation and the topic addressed. As you mentioned at the beginning, the energy efficiency issue is very closely linked to the current trends in terms of naval engineering, where we want to contribute to the worldwide objective of streamlining transportation, understanding maritime and cargo transportation as a huge contributor to this objective of decarbonizing our environment. This is specifically relevant for cargo transportation vessels, for cargo vessels. Okay, let's open up a Q&A session so that attendees can ask any questions if so they wish.
Que de pronto me gustaría escuchar y compartir.
Okay. Probably in terms of expanding the information on the basis of the hull that was studied, which was already taken to a race in 2017, did these results of aerodynamic resistance in terms of the dead weight of this race hull, how can you redesign this aerodynamic model of the hull? That's the first question. The second one is if in the study you consider the wind entry angle that is totally parallel to the drive resistance of the vessel hull, or if you've considered directions opposite to the drive resistance, maybe a perpendicular direction of the wind. Those are my two questions. Okay, thank you so much. Okay, if we can get some information. Okay, as I told you with the slides, our group has only covered unmanned vessels, so the amount of air draft is actually low. So how can we consider drive resistance generated by air in the designs? As you could see in the control boxes, literally those are elements. They're flat walls that collide into the wind. It's very difficult to actually go into the binding elements because we're using very simple elements there. However, back in 2019, we started building a manned vessel to participate in the Monaco Energy Boat Challenge, but because of COVID-19, it was canceled. Now, we were designing some type of body for the accommodation for the pilot or the driver, but due to COVID, the race was canceled, and we're actually planning to resume this project. As for the second question that you asked, no, in this simulation, we only took into account the the wind hitting the water in a parallel manner at a parallel speed and at the same magnitude as the water, considering that the air is still, which is not a real case, that's another restriction that we need to change in the model, in the simulation, and we'll take that into account for further studies.
Muchas gracias.
Okay, thank you. Let's wait a couple of minutes. Questions can actually be put into the chat room.
En este momento estamos en un corte, o sea, breve mientras que consigue las preguntas. Cuando consigue las preguntas me avisa y enseguida lo mando en vivo otra vez.
De acuerdo. Muchas gracias, Johan, por tu intervención, por la ponencia que nos trajiste. Gracias por las respuestas que ampliaron un poco el tema que trataste en la charla. Y pues esperamos que siga siendo una participación masiva del grupo de investigación de hidrómetra en este evento para futuras ocasiones. Muchas gracias.
Muchas gracias a ustedes por el espacio.
Gracias.
Listo, muchísimas gracias a todos, estuvo bastante excelente.
Muchísimas gracias, hasta luego.
Hasta luego.
Buenas tardes. Vamos a darle continuidad a nuestra jornada de la tarde del segundo día de ponencias en nuestro congreso, enfocados en el bloque de diseño y construcción de buques. Para cerrar la jornada de la tarde de las ponencias técnicas, invitamos al señor Edgar Steven Chávez de la Universidad Nacional de Ingeniería de Perú. El señor Chávez es ingeniero naval de la Universidad Nacional de Ingeniería del Perú. Cuenta con experiencia en diseño naval y análisis numérico de embarcaciones. La ponencia que trae a nuestro evento se titula Simulación numérica de una prueba Sea-Row para una embarcación pesquera. Les dejo en compañía del señor Edgar Steven Chávez.
Muchas gracias a la organización en general, a todos, a usted por la introducción. Y bueno, sí, procedo de la Universidad Nacional de Ingeniería desde Perú y voy a presentar este trabajo relacionado a la simulación numérica de una proa de una embarcación pesquera.
Regarding numerical simulation of sea-row for fishing vessels, adapted as a new proposal of a design that is used within the fleet of Peruvian fishing vessels, and this work has been developed together with 9 Jose Rogero engineers with a wide experience regarding simulation in the naval industry here in Peru. First of all, make as a preview so that you can understand very well what's the core and the content I'm bringing to you this afternoon. Then I'll be talking about the methodology, and later on the results and some comparisons of doing and final conclusions at the end. So firstly, talking about the fishing industry in general, it has several problems. One of which we can mention, everything's very conventional. They're not really fond of innovation. That's why up to date we can see very old designs based in a whole design that's the one that was used, that has been used, and then replication of that over and over. So that results in very deficient models. One of them we can mention, for example, in the local industry, we have a lot of vessels. Is this one that I'm showing there? It's a group ball vessel that really improves resistance in moving forward when we are working very shallow draft. But we have to keep into account that fishing vessels work in different low conditions with variations from the departure from the port to the end.
De 2 metros aproximadamente el calado, ¿no? Entonces, si yo estoy diseñando un bulbo para
we have to see that they're all returning to research, and we have done some experiments. Obviously, the results have not been the best for a higher bulb vessel that results in performance in this when facing these situations. So it is also important here in our country. For example, here in Peru, we don't have trade access to a hydrodynamic channel. Many times, law has to be taken to channels in Chile, Brazil. So access that increases the costs. So the studies are really basic. So when we see a work of a fishing vessel facing this project, we have carried out resistance study, something that is really good nowadays, and thing that we see that we see nowadays, but that's just an opinion. There's nothing we can see or evidence to say that the model we see that it's a model very well known, an American one, and it has brought to this part of Latin America by the end of the 90s, and up to today it's still in use. What has been done inside in its bulb, but some modifications have been carried out. Modifications that they have not written to them do with this model. Okay, we have the arrow bow. The arrow bow means a sharp angle bow as an arrow. It means a bow with an inlet angle. In our arrow bow, what did it all come from? It came from a research done by Japanese, and they got to obtain the resistance of the advance more than 7%, with the requirement of engine reduced in 7%, which is very advantageous regarding big draft vessels. We see it was possible to bring it because the draft was not constant, but was variable. And another reason is that it were different speeds or intermediate speed to low speeds, which we have similarities. So we proposed this model to adapt the adjustment. We carry out different designs based on the models with better results were taken. Okay, this regarding the design, the chosen pattern was a 14 prototype, and you see the difference. I need to highlight that Ciaro has three main features. The first one, the straight bow from beginning to end. The second feature is not the same as a ball of bow, but it compensates with the bow with that straight. In a few words, the difference in displacement of a vessel compared to another vessel, it must be slight. Light means less than 1%. And then as a third point, the inlet angle. The inlet angle must be more reduced than the former one. So we're talking about an average of about 15 degrees in the inlet angle. So we concluded that the vessel presented here was the framework, and then we changed the 9.5 meters of the bow module, having like this a total of 21% of the vessel that was being modified. And after being modified, we got this data variation of 4.8% in displacement. So you see 1 ton, the difference 0.1 was the variation. This was all taken in high draft. These are some of the data. The most meaningful one was the one regarding the inlet angle. And this is the model, the way it was proposed. It's Marine Seattle boat. These are the features it has with 44.7. Only there's a difference in the mirror, diagonal one, and there's where there are some centimeters in difference. The draft difference kept in the placement and wet surface. Let's take a look at the numerical analysis. But the numerical analysis, we used a computational tool. First, we are going to define our computational domain as it was explained, we always based in the guidelines provided by ITCC. They have a specification taking this four head, one at the bottom and half to the top, dividing from the floating line. Then we have the mesh. For the mesh, we use polyetheric mesh, obtaining also inflation layers, which are made with prismatic mesh-like. And what's interesting about all this is the free surface. We have the free surface, very well defined, with smaller items, so that when we find our waves, another interesting item is the detail of the bowl. When we have a very fine bowl, inflation layers didn't get to its place, as you can see in the upper right corner. It didn't have inflation layers; they were very small. So, in order to go, when we ended up refining this part of the mesh, as you can see, the size of the item of the hole is different from the element of the bowl, and we took a higher or a bigger. However, the size of the inflation layers was obtained, verifying the results so that we could get that direct captation of the phenomenon occurred in the limit layer. This is regarding the mesh. Here, boundary conditions at different speeds. We're showing at 8 knots in both inlet and outlet. This is inlet data for both the software and SID, and obtaining always symmetry. Regarding the result speed, you can see speed of the Seattle for 12. You can see how it is coating the part of the bowl, very pointed, like cutting. What we're going to see here the most is that we reduce the first wave a lot, and we're reducing a lot, just producing 2 waves with a very long shape tendency. That's what's important here. Regarding data, we carried out analysis by a whole trop of system, and it provided ideas about how to see and how it was going. And basically, we used this kind of theories and others to get the tendency of how our group is making progress. It is true in numbers, maybe it's not going to be so accurate, but regarding time, it can help us to get to know the tendency of a result heading to one result. However, when we see from the numbers point of view, we see there are high differences, higher than 15%. So it's recommended for a final result to get a CFD model to get to analyze results with details. So we see other components of the drag force regarding friction and wave formation, where we can see that wave formation is no higher than 40%, because this model has tried to reduce this part of the drag force component, just having the component of friction. Here we can see comparison of the 2 vessels, not only with both, but with the Seattle Pro Bowl. and you can see there's increase, and the increase goes down. You see elevation of the angle generated in a bowl with bulb with a higher a major draft, and you see that when we have an angle that's higher, when we can see that the wave it's lighter, and you see how the wave it tends slightly down when we work with a more angled bowl. So comparing the resistance, you can see this chart, which shows how much reduction we get. We haven't assessed the point, because in this range is the ones these vessels are driven, the most common 11 to 12 knots, and you see that at the same amount of resistance to the advance, we get almost 1 knot in favorability. We have augmented only 1 knot, while we have a pre-established engine. So if we get, we're gonna 12 knots, which is really meaningful to advance 1 knot in this kind of vessels. That's very meaningful regarding economy of the shipyard and the fishing company. For conclusion, mathematical model used was a turbulence model, K omega. This criteria was validated. It is important to highlight that before we carry out this kind of simulation, we first contrasted the results with the trial with bulb in a trial in channel that we had already done, and we brought these results from another thesis in our university, and we compared the 2 results, finally obtaining a little mistake of 3% for the indicated speed, which validates our simulation and told us we could use this method to assess the Seattle with some consideration regarding the mesh that I told you about before. It is important to see the different regions. We have a region with Prisma regarding inflation layers, and this all comes by a recommendation for ITTC in this kind of analysis. Finally, it is always to highlight and making comparison in the whole drop method, because there is a mistake that's being as high as 35% in higher speeds when we have a number and the holder starts to go away from the real result. And that's something that we have assessed as well in the channel trial, and we could compare this relationship. Finally, this analysis of fluence being useful to simulate this kind of vessels, getting a final reduction up to 25%. And this all tells us that if we continue with these studies, we're going to get reduction in cost, and we be able to come up with the proposal that's with high performance. And we have to continue with these kind of designs in order to improve quality of fishing in the region, and that'll be a contribution. And a part of this, we are also planning to start with simulations with other kind of boats. And the design equipment team is also thinking about it, and we are thinking of an optimization, including adding some more artificial intelligence and work hard in our networks. This would be the end. I'll be open to answering to your questions. Thank you very much.
Muchas gracias, Edgar. Esperemos unos minutos que el retraso entre la señal que tienen desde la charla de chat con la que tenemos acá desde la sala de moderación. Entonces, demos unos minutos a que el público pues escuche hasta el final la charla para que formulen sus preguntas.
Ok. Sí.
Mientras esperamos, que existan las preguntas desde la sala de chat, me gustaría formularte un par de comentarios para de pronto tener un poco de
have a few comments for you so that we can like depending on the information and regarding the future use you can give to this study. The first question is related during the talk you mentioned that there was a necessity to modify the hull in about 21% of the genuine vessel. Is it possible to extrapolate this to a work level so that we can make a conversion or transformation of a bowl with bulb or saddle? That was one of the questions. First, if it's possible, or if we have an indication that it's necessary to intervene that same percentage regarding 100% of vessel in order to make a whole transformation in a vessel with this kind of bows. And the second question is connected to this one, in case that this formulation can be used to come up with a new line of vessels design that maybe is more interested in this kind of procedures. What would be the assembling advantages, gaining more speeds in knots? They can carry out their tours in less time because the speed's less, or what could be more interesting for them to lose some power to provide engines with less power, so that'd be a reduction cost. That'd be my question.
Muy buenas las preguntas. Sobre todo es un tema que estamos manejándolo junto con el ingeniero Rollero.
Okay, it's a topic that we're handling with Rollero, engineer, who's a member of the team and he's really expert in this. So just this model we have talked about here in Peru, we have more than 10 vessels with this kind of a pattern, and some of them regarding shape and design is the same. We are carrying out modification in 9 meters. Generally, these vessels are handled in 8 to 10 meters modules. We are just working in the bow module. We're starting to carry out the economical analysis, not only referring to the engine. When you are carrying out modification, you don't want to change the genuine machine. And the idea is that with the same machine, you can get results. And with this in mind, we can get better performance in energy, so that I can carry out a tour of fish in 7 hours. Now I'll be able to carry a fish in 6 hours, consuming less fuel. If I used to do it with 100 gallons, now I'm gonna do it the same tour with 80. That's gonna be the main advantage regarding cost, the save of fuel. That also will impact positively the environment. And currently, they have asked us a lot about the model, and they have asked us to show anything regarding economical analysis, and they have asked us to present it as an economical proposal. But now we have done for one draft, but the idea is to carry all the process for the 4 operations that a fishing vessel has, and show the 4 conditions, and show that all the resistance have been reduced, and we have gained more energy through this new model. Thank you very much. It is understood that the modification for this kind of procedure is more like adapting the bulbs of bow, comparing with the performance of energy. I think it's very accurate in your proposal. Within the talk also you mentioned an item that you had data of the real holes of these type of holes, of these kind of vessels. Did you have access to results of channel trials of those vessels? What reference information did you get in order to validate your aerodynamic model? Thank you. Good question. Thank you. Okay, we have the information, the data of what was done in the channel trials, and this was all collected by a graduate student working his thesis. When we were starting the analysis, we kept this model and coordinated that this model was the adequate for this project, for this channel trial, and in different conditions. And we chose that in order to come up with the comparative approach and validate our design. Now we are talking about Seattle, but in the trial with Bulb, we have some challenges. But now we are trying to perform our own channel trial regarding trying to work with this kind of holes in order to carry out this analysis. Thank you very much, Edgar. Here I got a few questions from the chat. First one has to do with what methodology was used to assess the quality of the mesh regarding the model of the vessel, if there was any convergence analysis of refining of mesh during the process that maybe was not included in the presentation. But I would like to know if there was any refining process of meshing convergence. And the second question has to do if you carry out assessment of the constructive aspects regarding the type of bowl, keeping in mind that there's a complexity associated to the construction of a bowl like that one refined when finishing the boat. Answering the first question, yes, we have had several criteria to face this topic of choosing the best mesh item. Shows the kind of all the elements we have, all the items we have, and we tried with the mesh rig to the final point when we got the polyetheric one. Why? Because we are always trying to fulfill requirements, because we have the interactions, and this model has gone through 10,000 interactions. So I think the K, so this also is a criteria that shows us that the simulation is on the right path when we see the convergence with the convergence criteria. And regarding the second question, constructive analysis, it's true, it's a model a little bit complex to carry out. However, we have assessed yacht models with tire trials, which are very similar and have been built in several vessels. So what we have assessed is basically we did some sections cut in sections, and in those cuts we assessed the altitude based on the distance between layers that we were going to use in certain places, the dimension of the layers, and from that we could carry out some corrections regarding design. But this was the way the constructive LP was assessed. We carry out that analysis of the section that we had in different parts. Each half meter was what we carry out evaluation. So we hope to carry out a structural analysis as well. I agree. I think when projects become conversion projects, when shipyards come to take part of the modifications, then there will be restrictions for the refining and the possibilities that these projects will have. In that case, the study must have the dimensional because at a certain value it will be difficult to build an element or a structural block. So at a certain point, we'll start to have more data. So it also depends on the shipyard. Each shipyard has their own criteria. So I think when designing the study, then we have to keep into account the considerations of the manufacturing when carrying out the analysis. Yes, I strongly agree with you. It's exactly how the project is making progress. Okay, Edgar, right now I think we finish this
por el tema tratado. Creo que
talk. Thank you very much for your devotion for this topic you have been dealing with in this blog focused on the design of vessels and naval design. I think it was a really good reference to start this blog, and thank you for your participation, and I hope for our future sessions you can come and continue contributing. Thank you very much. Thank you, COLOMBIAMAR and the whole organization.
Que tengan bonita tarde todos.
Muchas gracias. ¿Podrías conectarme ya?
Sí, ya todos se pueden desconectar.
Bueno, vale, muchas gracias.
Listo.
Muchas gracias, buenas tardes.
Hasta luego.
del comercio mundial se mueve por vía marítima, por lo que durante la pandemia los puertos tuvieron que mantener su operación para garantizar la cadena de abastecimientos y los astilleros continuaron trabajando para garantizar que todas las armadas del mundo continuaran cumpliendo con su misión de defensa y seguridad, y de igual forma que las flotas navieras siguieran moviendo la carga a nivel internacional. La emergencia generada por el COVID-19 también nos ha llevado a reflexionar sobre la importancia de la autosuficiencia y la independencia tecnológica, y es precisamente por este motivo que nos vemos convocados el día de hoy. Es así que en escenarios como este se hace evidente la necesidad de apostarle al fortalecimiento de los sectores productivos y las cadenas locales de valor como aspectos relevantes de las actividades marítimas, así como la adopción de la transformación digital en la industria astillera, los desafíos y las estrategias para la apropiación de nuevas tecnologías, el mejoramiento y eficiencia en los procesos de construcción naval, vehículos no tripulados y el uso de energías alternativas que implican nuevos retos en términos de diseño e ingeniería naval en Latinoamérica. Lo anterior nos compromete como industria astillera a continuar con los compromisos adquiridos en los pactos por el crecimiento y la generación de empleos en términos de inversión, generación de encadenamientos productivos y sofisticación de nuestra oferta exportadora de alto valor agregado, con el fin de potencializar la competitividad del país a través de la independencia tecnológica que otorga esta industria a un Estado. Asimismo, estamos comprometidos en seguir desarrollando una oferta de soluciones tecnológicas de impacto social para darle respuesta a las necesidades básicas de nuestro país y de la región en temas de salud, educación, logística y transporte de las poblaciones ubicadas en los lugares más recónditos del país, a los cuales solamente se tiene acceso por vía fluvial o marítima. Hoy culmina esta versión digital de COLOMBIAMAR 2021 con el desarrollo de exitosas conferencias magistrales, 2 foros, 20 ponencias técnicas y la participación de más de 2.700 personas conectadas a nivel nacional y alrededor del mundo. Estoy seguro que estos debates científicos e intercambio de conocimiento en el marco de una intensa agenda académica y científica han fortalecido las relaciones entre todos los actores de la industria astillera nacional e internacional. Aprovecho la oportunidad para invitarlos de forma anticipada a COLOMBIAMAR 2023, que se desarrollará en el marco de la conmemoración del Bicentenario de la Armada de Colombia, evento que realizaremos en la hermosa ciudad de Cartagena de Indias, Colombia, deseando que tengamos la oportunidad de seguir estrechando los lazos académicos, científicos y comerciales en medio de tan esperado regreso a la normalidad y la reactivación económica del país, la región y el mundo. Muchas gracias a todos.